Right now, though, we need to get started with a brand new unit called Chapter 7, which is Work and Kinetic Energy Theorem. So this is still, we are still on the launch pad as far as basics are concerned. So let me know, you guys, if you're seeing something different than I am. I am thinking that this is what Chapter 7, Quiz 1 looks like. And I might be incorrect with that. So let me know if you're seeing something different. And what I mean specifically, this is the foundation. This is the core of physics and engineering. I would say this is the core of physics and engineering: motion, force, work, energy. Everything is built upon this foundation in terms of, again, subsequent physics classes, which many of you might not be taking. Many of you won't take any physics class after Physics 211, Physics 212. So Physics 212 is probably, for most of you, the end of the line. Some of you will take additional physics classes. All of you will take additional computer and engineering courses. And this claim still applies. Motion, force, work, and energy is the foundation. And here we are right now. We are here. This is Chapter 7. And this is basically Chapter 7 and Chapter 8. So we have taken a first look at motion and force. So make sure you guys, you just keep on applying yourself. Let me just call up. Let me just point you guys. Let's point at this exam right here. This was the exam you took right here. So let me say this. If any of these questions look alien to you, or if you literally couldn't provide much at all in the way of a solution, you're in category B. You are officially standing in category B if any one of these questions looked odd, looked unusual, looked foreign. And here's question 1. Here's question number 2. Here's question number 3. And here's the good news for you guys. These are all remarkably consistent with the homework. So if you're in category B, it means you're here on Tuesday for the Zoom session. You're probably getting most of these quiz questions correct, but you're not deep learning. So this is the keyword for today. The keyword for today is you need to do more than just collect your quiz points. You need to actually do some deep learning, because, and you know when you've deeply learned all of this stuff, because when exam 2 happens. On exam 2, you're going to look at another set of questions that won't be out of the blue. Have you ever taken an exam where the exam questions look utterly alien? They're not at all familiar to you in terms of what you did in class or what you did in quizzes or the homework problems. That is profoundly not the case here. So I think a few of you guys might have gotten a perfect 100% on this exam. There were a number of really good scores, which is why I'm more in a good mood than I'm more in a concerned mood. But there were some number of you who literally were just, it's as if you literally didn't come to any class. It's as if you started Physics 211 on the day of this exam. It's just, everything just you seem to be lost. And yet, how can you be lost on any of these questions when they're so easy, and yet still get full credit on the exams and get full credit on the quizzes? So that's the drum I want to beat. You're going to get the right answer on this quiz, but you can't stop there anymore. You actually have to learn what's going on, because it really is. I mean, it's pretty obvious what's happening. If you're getting quiz points, but not able to answer an exam question, which is remarkably similar to a quiz, you're not learning. You're in category B. And the goal is to transition to category A, which is the category inhabited by the deep learners, meaning the people who are going to do well academically and professionally. So the goal is to get you to that level. Here's our first question. Chapter 7, quiz 1. Okay. You've watched the lecture video. And if you haven't watched the lecture video, again, you're still in category B. Because if you watch the lecture video, you know chapter 7 is all about how kinetic energy is 1/2 mv squared. And there's something called the work kinetic energy, which I'm writing down. That's the work kinetic energy. This is in the Hall of Fame. This is sort of in the same category as F equals MA. Okay. What else was a key part of chapter 7? This was a key part. The definition of work itself in general is the integral of F dot dr. And then this thing right here, you could actually make a case that maybe the single biggest takeaway from chapter 7 is this little punctuation character. This is dot. This means dot product. Some of you might be familiar with dot product. Some of you might be familiar with cross product. Dot product means the following: product of parallels. So I'm gonna spend kind of like a lot of time on the dot product, because not only do you need it for this chapter, you need it for other classes that go beyond physics 211, which includes engineering classes. So this is a big takeaway. So those are the highly distilled takeaways. There's kinetic energy, the definition of work, something called the work kinetic energy theorem, and maybe the hidden contender for the number 1 ranked most important piece is the dot product. Okay, so before we get into this problem, just dot product. Let's just say, for the sake of conversation, let's just say you have a box sitting on a floor. Here's a floor in your basement. Here's a box sitting on the floor in your basement. Actually, let's, okay, that's fine. All right, so you walk up to this box and you decide to pull on it with a rope. So you're applying a tension force that looks like this. So this is some tension force that you're exerting on the block, and it's a vector, and the block moves. The block moves across a certain displacement, which looks like this. Here's the displacement of the box. The box moves from here to here. Okay, so let's label this. This is just, I'm going to call this just some displacement S. S for displacement. You could say, why don't I call that X? And the answer is I could, but I'm calling this S for displacement. And the angle between the force you apply and that displacement force is theta. So that's what you're doing to this box sitting on a floor. You're dragging it along the floor via this force, this rope that you've attached to the box. All right, so now here's the question. How much work do you do? So here's the definition of work. Work is defined as the dot product of this tension force, F dot dr. So there's a generic definition of work. Specifically here, I'm saying, okay, if that's the definition of work, well, specifically I have the tension vector, that's my force, dotted with ds. Okay, that's what I'm doing. And here's the good news. The horizontal component of this tension force is doing the work. So check it. I'm going to draw, let me do a projection. If I project this tension force onto this displacement force, it looks like that. All right, so here's the X component of tension. It is this right here. It's a little bit too thick. So we're decomposing. So again, with the decomposition, this is T sub X. T sub x is the x component of tension. This is T sub y, the y component of that force. So I am done decomposing. I have decomposed this tension force into its components. And let me just say this, you guys, you're going at some point, whether now or when you watch the recording, you're going to need to understand everything I'm saying because it shows. It shows. One thing about these exams I learned, you can't really fake your way through it. So it does pay to really understand everything I'm covering here and in the lecture video. All right, so here's the bad news. Bad news is as follows. You've wasted this much force. This force, T sub y, this does no work. This does no work on box. No work on box. So that's a shame. It's a shame that you're exerting that force, and yet it does no work on box. This force, on the other hand, this does do work on the box. Because the box is moving in the plus x direction, and this T sub x force is also moving in the plus x direction. So to figure out how much work is done on the box, I need to multiply that orange vector. I need to multiply this highlighted orange vector. This is T sub x. I need to figure out what is that component, and then I need to multiply it by the displacement, which is this vector I'm highlighting here. Okay. All right, those are the two vectors I need to multiply together. You guys know from middle school, you've probably noticed this. Maybe some of you have. You know that you kind of learn everything 3 times. You learn chemistry in middle school, high school, and then again in college. Typically, if you're going into science or engineering, that's true. The same is true for physics. The same is true for a number of math classes. So you guys have all seen, you've all heard this statement before: work equals force times distance. That is for sure taught in the 8th grade typically, and then again in high school, and now again for a 3rd time. So all we're going to do sort of for this chapter is we're going to formalize this. Work is force times distance, and specifically work in this case is force. So let's formalize this. It's the force in the same, let me say this. It's the force that's parallel or anti-parallel to displacement times displacement. So this is a more formalized statement for what work is. Times displacement. Let me read through that again just because it sounds so darned useful. Work is the force. Let me add that. Just let's do some wordsmithing. Work is the force that's parallel or anti-parallel to displacement times displacement. Okay, and that's what I'm showing here with these two vectors. Again, that was the red vector, and this is the orange vector. So that's me. That's me calculating work. I'm specifically saying I'm going to take this T sub x vector, and I deleted that. This is T sub x, and I'm going to multiply it by this displacement vector, which is this red S vector right here. Okay, so how best to do that? Well, okay, if I do that, I'm still dwelling on this sort of this is like the warm-up part. We haven't even started solving this question. All right, what's T sub x? This was theta. So if I go into trig mode for a second, cosine of theta equals side adjacent T sub x over the hypotenuse. T, and again, this was T subscript x. So you guys by now should see, okay, I got it. I know what cosine does. I know T sub x equals T cos theta. So there's my answer. The work done in this case is going to be force. Here's the force. Here's the force that's parallel or anti-parallel to displacement. It's going to be T cos theta times the displacement times that S vector, the magnitudes. So here's the result. It's going to be magnitude of the force, magnitude of the displacement times the cosine of the angle between them. Because it's the cosine of the angle between them that captures the parallel or anti-parallel projection. Cosine gives me T sub x. Even if T sub x was pointing in the exact opposite direction, cosine would give me that. All right. So that's our first step into the dot product. Let's actually solve this problem with all of that in mind. And we're still going to have to get into some new things. All right. So now specifically for this homework problem, which is the quiz problem, chapter 7 is 1. Okay. All right, here we go. We have three forces acting on this box. And the first question is, how much work is done? So at the end of at part A is saying, what is the net work? The net work is the dollar sign. Okay. All right, so let's break it down. Let's do the science and engineering approach. Let's break a hard problem into simpler bite-sized pieces. The net work done on that box, because that's what it's asking. During the displacement, what's the net work done? All right, so I have three forces. So force F1 is going to do some work. Force F2 might be doing some work. Force F3 might be doing some work. So I just got to add all of these up. Let's talk about force F1. The work due to force F1 is, ready? Here's the definition. Integral of F1 dot ds. And I better draw the displacement vector. The displacement, it says here, it moves leftward. So this box is moving leftward. So it's vector. We're still definitely doing a lot of vector stuff. This box is moving leftward, according to my problem statement. It moves leftward by 2.6 meters. So I start here. Maybe I'm going to call this. This is x equals 0. And then this is, I guess I'm calling it s. This is s equals minus 2.6 meters. Okay. So my box is moving leftward. What is F1 doing? So let's just play it out. Okay, so you're looking at the dot product form. This thing here that I'm highlighting in green, this is called dot product. Now I'm going to write down the exact same thing, but in an equivalent form. This is going to equals integral of F, which specifically now, it's the magnitude of the force. So the magnitude is F1 times the displacement, the magnitude of this displacement times the cosine of the angle between them. So this exactly follows from that first example that I covered up until a couple minutes ago. Read this, theta is always the same. Cosine of theta. What is theta? Theta is the angle between the displacement and between the applied force. So now you have to ask yourself, and the next step here, I really could make a recipe out of this, which I like to do, to be honest. It's the engineer in me. I love turning things into methods for obvious reasons. Having a method is better than no method. Having too many methods is a problem as well. But what's the F1 look like? I need to redraw that since I kind of covered it up. Here's F1. F1 is right here. That was F1. Okay, so that's F1. Now you have to ask yourself, what is the angle between that force and that displacement, and theta equals 0. So now we can write theta equals 0 degrees. There is no angle between this applied force and this displacement vector. And I better indicate these are vectors. Okay, this is my S. This is my displacement vector. Theta equals 0. Okay, let's keep going. Here goes step 5. So the work done by force 1 equals the integral, and I better specify limits of integration. I'm going to do from 0 meters to 2.6 meters times F1, and F1 is given to me. It's actually given, my number is 4.76 newtons, yes, times S. So that's, I better call this ds. I'm going to have to call this vector ds times cosine of 0 degrees. So let me make a little update just to be airtight. I call that S. I should have called this ds. So let me just do that. Critically important update. This is ds. Okay. So let's make sure I have my head screwed on straight. All right. This applied force is 4.76. Just double checking it is. ds here, that's my variable of integration. So there it is. Can't do an integral unless I have a variable of integration. Theta is, as discussed, 0 degrees. It's good to know. Now here's a question. Shouldn't I say from 0 to negative 2.6? Shouldn't I be adding a negative here? And the answer is no. I shouldn't, because that's what cosine theta does. Let cosine let cosine produce the correct algebraic sign, the correct sign. Let cosine do it. If cosine is greater than 90, it's going to be negative. If cosine is less than 90, it's going to be positive. So that's what I'm going to do. So your job when dealing with dot products, your job is just to do what I did. Your job is to say, okay, I'm going to take the magnitude of the force. Got it? I'm going to take the magnitude of the displacement times the angle between them. And then in terms of my limits of integration, it's always going to be the smaller number as my lower bound and the greater number as my upper bound. So let's just cookie cutterize that right now. Let's just make that the convention. It's good to be consistent. Cosine will figure out positive or negative. Cosine will figure out if it's positive work or negative work. Okay, so number 6, this is like the world's simplest integral. That's good. The work done by F1 is going to equal 4.76 newtons times the cosine of 0 is 1. Cosine of 0 equals 1 times the integral of ds. So the integral of ds is s, and I need to evaluate it from 0 to 2.6 meters. So when I do that, this is how much work force F1 does. I've got 4.76 times 2.6, or 12.376, and that's a positive number. 12.376 joules. That's something new, but I'm going to double check. 4.76 times 2.6 is 12.376. New unit. So new unit alert. Attention. New unit alert. We have the following. 1 joule is defined as 1 Newton times meter. This is the unit for work and energy. So if you're calculating a work result or an energy result, the units will be joules. Or you'll get into this later. It could be calories or it could be British thermal units, but for now, joules. 1 joule. 1 joule. Named after a physicist. 1 joule is 1 Newton meters. Okay. So this is doing positive work. F1 is doing F1, vector F1 does positive work. So let's do the same thing for F2. F2 is going to go very quickly. No, it's not going to go too quickly, but let's do a F2. So let's put this, let's stick a pin in this. This is the work due to F1. Here's the work due to F2. The work due to F2 is, I'm going to go, well, I'll do it like this. Here's the dot product version. F2 dot product with DS. And then I'm going to say, well, this is equivalent to the magnitude angle. That's what I call this. What is the magnitude of F2? What is the magnitude of DS? What is the cosine of the angle between them? Which begs the question, what is the angle between them? So let's go back to your drawing right here. Let me get rid of F1 since we've dealt with, you're done. We have cooked F1. Here's F2. So specifically, I am saying, what is the angle between the displacement and F2? So I am looking precisely at this angle right here. I better call this, I'm just going to call this angle A since theta's already been used, which means, so angle A, which means I'm going to change this because I see theta's already used. That could be confusing. I'm just going to call this angle A. And then the question is, what is angle A? Angle A equals 180 degrees minus theta, or when my calculator is turned on, 180 degrees minus 60 degrees is 120 degrees. So that is a 120 degree angle. And I guess we're good to go. Same limits of integration. And remember, let's always use the lower displacement value, the lower position as my lower limit, the lesser position, the smaller number, the smaller position number as my lower bound, and the greater position number as my upper bound. And let me sanity check all this. Okay, so this is referred to as, this is the magnitude angle, or I just refer to it as magnitude angle, and this is dot product. So they mean the same thing. And now you know why they mean the same thing. Assuming you do the deep learning task. All right, so let's keep going. Step 8. Okay, the work done by that F2 vector is going to be the integral from 0 to 2.6 meters times F2. F2 for me is 9 newtons times ds times cosine of 120 degrees. And when I do all of that, I get a number. Well, I'm going to pull out the constants. If I pull out the constants, 9 is a constant, so it can come out of the integrand. Cosine of 120 is a constant. It can come out of the integrand. I'm left with the integral of ds from 0 to 2.6, and I know how to deal with that. So what is 9 times 2.6 times cosine of 120? Negative. It's a negative number. Negative 11.7 joules. This is the work done by F2. Okay. It's doing negative work. What's the difference between positive work and negative work? We'll talk about that a lot. But that's my value for F2. I did 9 times 2.6 times cosine of 120. All right. Last but not least, F3. F3 looks like the weight force. F3, I think, is the weight of the box. The work done by F3 is, watch this. Well, this is the standard operating procedure. I'm going to go from dot product representation to magnitude angle representation. So that's the magnitude of the force, the magnitude of the displacement, cosine of the angle between them. I'm going to call this angle B. What is the angle between this displacement and that force? This is angle B, and you can see angle B is 90 degrees. So B, angle B, do it over here, B equals 90 degrees. And you know the cosine of 90 degrees is 0. So F3 is not 0. F3 has a value. It's 3.08 newtons. But despite having a value, it's not doing any work. Cosine of B is the cosine of 90 degrees equals 0. So therefore, the work done by F3 equals 0 joules. So that's it. Now all we have to do is add them all up. Here's the result for the work done by F3. This was the work done by F1, and then the work done by F2. Let's add them all up, because number 11, the net work done on this box equals the three of them added together, just like I'm writing here. Okay. Negative 11.7 plus 12.376, 0.676 joules. All right, and that's the answer. That's the answer to part A. There's more parts. This is the answer to part A. Part B says, that's A. Part B says, is there a net transfer of energy to or from the trunk? So this is a convention question, and you'll get this. And again, if you have not yet watched the lecture video, you're still a resident of category B. Why don't you come over to category A, where the sky is blue and the grass is green, and watch the lecture videos before showing up to lecture? Because the convention, this is a convention issue. Convention. Is there a net transfer of energy? Positive work. Positive work, meaning if work is greater than 0, means objects' kinetic energy increases. So that's actually the answer to part C, but this is sort of a convention thing. If I'm doing positive work, the object's kinetic energy increases, and then I would say work is, or energy, I should say, energy is transferred to. Energy is transferred to the box, to the object, transferred to the object. That's what it means. This is the takeaway. This is the takeaway for having a net amount of work greater than 0. 0.676. It's not much, but it's something. This will increase this number right here. This will increase the kinetic energy, and it's basically a way to add energy to this pink box from some external force. That's what you want to do. Okay, just like an automotive engine transfers energy to the automobile through energy transfer, transferring stored chemical energy into kinetic energy. That's it. Done and done. So this is our very first Chapter 7, kinetic energy problem. I'm going to go set up a quiz, but you guys, I need to start hammering this point now. You guys, you probably already have gotten this question completely correct. I'm assuming that you already have this completely correct, or you are moments away from getting it completely correct. But now here's what you have to do different. Not all of you, but a good number of you. This is what you have to do different. let's really think about this carefully. Look at everything I did. And I'm not saying you have to do it now. Maybe you should do it now, but I'm saying, hey, when you rewatch this lecture video, which again, if you're not the kind of person who rewatches lecture video, you are still a possibly content member of category B, but you got to do that. You got to watch the lecture videos before class. You got to rewatch the recorded Zoom sessions at least once or twice, because without doing that, there's no way you're going to do the deep learning. There's no way. So I'm going to get quiz 2 ready to go. Quiz 2 is problem 16. So let me get quiz 2 cooking. Our next quiz. All right, chapter 7, quiz 2. Give me another moment.
Hey, Professor.
Yes.
Are we going to go over more chapter 6 on Thursday?
I don't know. Why?
I was doing the chapter 6 homework, and a lot of it was like the stuff we did in class before the exam. So like that I was getting used to, but there were some problems where there was like you have to add the radius and stuff like that that were kind of tripping me up. So
Like
I was wondering
the centripetal stuff?
yeah, a lot of the centripetal stuff was very I don't know, it just took a long time, and like I didn't feel like we did any of that.
No, yeah, the answer is we can, but every so often, Ali and everyone, every so often, you might kind of need to try to solve a homework problem without, getting the solution handed to you ahead of time. Having said that, that's what I do. I basically hand you the solutions to almost every homework problem via our Tuesday classes and the deep dives. But I think in chapter 6, there were 3 centripetal force problems. One of them was done in a deep dive, which meant you were kind of on your own for 2 of them. So that we can talk about that. We can talk about that on Thursday, is because centripetal force really, it turns out to be a big deal. I mean, there were centripetal acceleration problems in chapters 4. There's centripetal acceleration and centripetal force problems in chapter 6. And it turns out we're probably going to spend more time on that type of world, the centripetal world, than we are on the linear world. So I'll go back and we'll check out those problems on Thursday for sure. So that really is a good idea. Okay, so I'm going to, what problem? Oh, this is chapter 16. All right, so problem 16. The other thing too is don't be shy in asking a question to the group chat, which means you need to get, this is the other thing that and I'll say this, you did well on exam 1, so I'm not talking to you. In general though, for those of you who are looking for ways to improve, start using your lifeline, start posting questions to the group chat like that, because that's what it's there for. And if you posting a question on Sunday night is probably not going to work. You need to be a little more proactive than that. So but use group chat if you get stuck and you feel like getting unstuck. before the homework is due. But you're asking the right question. Even though chapter 6 is already passed, we got to learn it. You got to learn every part of it.
Yeah, that's mostly what I was like asking about. I think there was one centripetal and I didn't finish all the way, but like I was just looking for explanation towards like for the exam, if those are going to be on the exam.
Yeah, for sure. Because again, centripetal stuff is arguably going to be more common to us than linear stuff. So that's why I'm very happy to review that on Thursday, especially since I don't think I've spent a lot. Well, there's been a decent number of deep dives, but yeah, more time the better. Because you're right. You're right. I mean, it's sad if maybe you lost a homework point here or there. That is dwarfed by your exam performance, which is why I'm always saying, do your best on the homework, but, before the deadline or after the deadline, one way or the other, do the deep learning thing. All right, so I think you're ready to go. Chapter 7, quiz 2. Let me know if your chapter 7 quiz 2 does not look like this. This is what I think chapter 7 quiz 2 looks like. We're still living in the world of kinetic energy and working. That's all we're doing. In many ways, chapter 7 is a pretty narrow chapter. The big takeaway is this dot product thing, though. That's just huge. So by the end of today, you're going to be a lot more familiar with the dot product than you were an hour ago. All right.
Not my problem.
It's not your problem?
Mine is like a chord is used to vertically lower a block.
All right, let me go fix this then. All right, chapter 7, quiz 2. I'm sure you're not alone.
Mine was just changed to the one that you have on your screen.
Okay. So maybe it's just a refresh.
Yeah. So I had to go back out and then come back in.
Yeah, that's
the right one.
All right, refresh. I'll refresh, Ollie, and let me know if there's still issues. Go out and come back in. Thanks for letting me know. All right, so here we have an object, the ubiquitous object. Here is an object sitting on a floor, I guess. An object on the floor. There. It's moving in the positive x direction. So here's my displacement vector. Ready, set, go. My object is moving in the positive x direction. This is why reading the prompt statement is so critical. Yes, I know the mass of the object. Yes, it's moving in the positive x direction. I'm reflecting that with this vector here, vector s. Got it. When it passes through x equals 0, so a trigger happens. This box passes through x equals 0, maybe like right here. So this box is hitting the x equals 0 mark right there, x equals 0. As soon as it hits x equals 0, when it passes through x equals 0, a constant force turns on. A constant force is activated, directed along the axis. So now here's a question. A constant force is activated. Is it pointing to the right? So here's the question. Is this force that starts to act on this object, is it pointing to the right or pointing to the left? And you know what? I'm actually going to say it's pointing to the left. And let's talk about why. I think this is the applied force, F. All right. When it passes through x equals 0, a constant force directed along the x-axis, but it doesn't say if it's plus x or minus x. So I think this is a negatively directed force. Why am I saying that? Because look at the graph. The graph. When my object is at x equals 0, at x equals 0, right at this moment, my graph says, here's how much kinetic energy I have. I have K, maybe I better call it initial. This is X initial. This is initial kinetic energy equals 25 joules. That's what my number is. That's what my problem says. 25 joules. And I'm looking at right here. Right here, when my box is at X equals 0, it has this much kinetic energy. This much kinetic energy is 25 joules. They're using K subscript 0. I'm using K subscript I. It means the same thing. All right. And then as this box continues to move forward like this, excuse me, the box moves to the right. And then apparently it's slowing down. In fact, it slows down and ultimately stops right there. How do I know that? Because look at x equals 5. At 5 meters, this is what's happening. At x final equals 5 meters, my kinetic energy, which I'll refer to as my final kinetic energy, equals 0 joules. And let's remember what kinetic energy is. It's 1/2 mv squared. So therefore, dot, dot, dot means therefore, V final equals 0. So it slows to a stop. My box slows to a stop. Okay, that's why I'm thinking my force is leftward. Because then, as time continues to tick by, my box reverses direction and starts to go this way. It's going from its stopped position over here, and then it goes way over here to negative 2.6 meters, according to my numbers. Let me just indicate that. All right. So this position, as I read my problem statement, this is x equals negative 2.6 meters. So that's a lot to bite off. Okay. And let me make sure. And then we need to know the speed. So V equals $sign at this point. All right. So I'm just going to replay this in my head just because this seems pretty involved. Let's see. All right. So my box moves to the right, slows down, comes to a stop, and then reverses itself. And at the x equals negative 2.6 mark right here, what is the velocity? Okay, so let's jump into it. This is a job for the work kinetic energy theorem. This is a job for the work kinetic energy theorem. A Hall of Fame recipient, work kinetic energy theorem. This is foundational. This is the work kinetic energy theorem. The net amount of work done on an object is going to equal that object's change in kinetic energy. Okay, so let's just run with this. Why do I think this? Just because of what I know. I know it's talking about a force. So they're talking about a force. They're talking about various displacements. And then I have a graph of kinetic energy versus position. When you read that, when you sort of digest all of this content, you are left with a conclusion. You're at least, at the very least, you're thinking this is work kinetic energy theorem. So let's go with this. All right, so here's the net amount of work. There's net work, F dot ds. Yes, this is the generic dot product, which I think I'm going to go from generic dot product to generic magnitude angle. And let me just highlight for the umpteenth time. This vector F dot product with vector ds is the same as F ds cosine theta. And whatever that is, that's going to equal the change in kinetic energy. And change in kinetic energy, delta K delta is always final minus initial. All right, so now what? And so this is me just brainstorming. Now what? So you could say, well, what does that buy me? Well, I do know some things. I do know some things from the graph. I know the kinetic energy at x equals 0. I know the kinetic energy at x equals 5. So this is my thought process. Find the applied force. This is what's sort of bubbling up in my head. Find the applied force, because when it passes through x equals 0, a constant force, they do mention a constant force is directed along the x-axis. So I'm going to go after that constant force. And once I know that constant force, I'm going to see what it's doing to my object at x equals negative 2.6. All right, so more specifically, the integral, I'm going to do from x initial equals 0 meters to x final equals 5 meters. This is the interval I'm going to look at. So at x, I'm going to use this as x initial, and I'm going to use this as x final. So I'm chunking things up into intervals, which is obviously a thing we've been doing a lot. This is x final equals 5 meters. At 5 meters, my final kinetic energy is 0 joules, according to the graph. At 0 meters, at x equals 0, I have this much initial kinetic energy. So, okay, these are all courtesy of the provided graph. Let's go ahead and keep hammering on this. All right, so I have the integral of f, that's my unknown, ds cosine of 180. Aha, much needs to be said about that. From 0 to 5 meters, this is, yes, I'm feeling, this is my displacement from 0 to 5 meters, that red vector S. So this red vector S is my displacement from 0 to 5 meters. From 0 to 5 meters, this is my F vector right here. So that's why I'm saying this angle is 180 degrees. Theta equals 180 degrees. And you can tell this force is doing negative work. During this interval, energy is being lost. This force is causing a loss in energy. So back to number 6, this is going to be from 0 meters to 5 meters. And then I guess I'm done, aren't I? I am. So, well, this is my change in kinetic energy, K final minus K initial. Okay, so let me just refocus. This is the total amount of work done across that interval from 0 to 5 meters by that force. It equals delta K. This amount of work is, I'm going back to here, that amount of work is equivalent to the change in kinetic energy. So that's why this is K final minus K initial. K final is 0. So this equals 0. K initial was 25 joules. All right, so number 7. Here's what I got. This F is constant. That can come out of the integrand. Cosine of 180 is -1. The integral of ds is just s, and I'm going to evaluate it from 0 meters to 5 meters. And 0 minus 25 is -25. So that means F, my F equals 5 newtons in the negative I hat direction. So I got it. I actually have a numerical value for that force vector. It's pointing to the left, and it has a value of 5 newtons going to the left. So now I think I can use that force. Now look at the interval from x equals 0 to x equal -2.6 meters. So let me clear the slate, because now this is a different interval. So I'm going to get rid of all of this because it's getting messy. You can go, you can stay. All right, you can stay. There's my F vector. This is now a different displacement. Okay. Okay. So now clearing the clutter. All right. I guess I can get rid of this. So the interval I'm looking at is from 0 to negative 2.6. So here's my displacement vector. My displacement vector is starting at 0 and going to negative 2.6, which is right there. There it is. This is vector, that's vector S. And then you have to ask yourself, what is that angle? What is the angle between green and red? That's always a question you have to ask yourself. Well, let me return to that. Let's do number 9. When I look at this interval from 0 to negative 2.6, I'm going to do the work kinetic energy theorem yet again. So, you know, that means I need to worry about the integral of F dot product with ds. And I'm going to just transition right to, we're not always going to do this transition. Later on, we're not going to automatically go to magnitude angle format. But for now we are. I think for today we are, but that's not always going to be the case. What's the magnitude of the force? What's the magnitude of that displacement? What's the cosine of the angle between them? And whatever that is, that equals K final minus K initial. Okay, so specifically, I have the integral of F, which is 5 newtons. So there's 5 newtons times the displacement. And this has to be my variable of integration. Again, if I want to do integration, I have to have a variable of integration. That's why I'm going from vector S to the differential form. Okay. Cosine of theta is cosine of 0 degrees because theta in this case equals 0. There's no angle between green F and red S. And my final kinetic energy is I don't know. So that's just going to be K final minus my initial kinetic energy. And when X is at 0, my initial kinetic energy is 25 joules. So I need to specify from 0 to 2.6. Again, I still, even now, I would understand if you have the urge to record that as negative 2.6, but that would actually be a mistake because cosine of whatever this angle is will take care of whether or not this is positive work or negative work. So this is always going to be some positive number. This is always going to be some positive number here, some positive number here. And it's the cosine that will tell you the correct sign. So let's solve for KF. We're almost done. KF equals 5 times 2.6. Turn it on. Okay, 38. My final kinetic energy equals 38 joules at X equals negative 2.6 meters. So that's huge because I know what kinetic energy is. Kinetic energy is 1/2 mv squared. So all I'm going to do is solve for V. If kinetic energy is 1/2 mv squared, then V equals 2k over m square root of all of that. Square root. All right, do I know K? Yes, I do. K for me is 38. I know the kinetic energy, the mass is given for me, it's 7.8. So when you put all of that into the blender, you get times 2 divided by 7.8, square root of that. Great success, 3.12. 3.12 meters per second. And you know what? we need to do dimensional analysis. This is no longer an option. You're going to always have to do dimensional analysis. So dimensions, I have V equals 2. So in my numerator, I have kinetic energy. Kinetic energy is given as joules. In my denominator, I have mass, which is kilograms. So what's a joule? A joule is a Newton meter. So there's my numerator. Here's my denominator, kilograms. So what's a Newton? A Newton is a kilogram meter per second squared times meter. That's my numerator. My denominator is still kilograms. And from this, you can see that my units are meter squared per second squared. So that's good news because I need to take the square root of that. So I need to take the square root of that, square root of that, square root of that, there. So I do end up with meters per second. That's great news. What a great problem. What it's worth. And it's worth a lot. This is the answer to, it's only a single part problem. This is my 3.12. Really, I'm trying to really hammer home incessantly how to deal with dot product and this whole work kinetic energy theorem. And you can see it relates to force. We have to have an accurate free body diagram. So let's do this. See you at 2:12. 2:12 p.m. for more kinetic energy fun. And that's good. See you at 2:12 p.m. Okay. Chapter 7, quiz 3. Onward. Chapter 7, quiz 3. Another ramp problem. Boxes on ramps, lots of those, just because it forces you to really decompose and analyze things. They're pretty complicated. But when you do enough of them, they're not too complicated. You have a block of ice. A block of ice. A block of ice is sliding down a ramp. So here are the details. A block of ice slides down a frictionless ramp. So we're not too far away from accounting for friction, but right now this is frictionless. We have the ramp angle. And while this block is sliding down the ramp, you're pulling up. You are actually pulling up on a rope. So it's as if you're trying to stop the box from sliding down the ramp. The box does slide down the ramp. So I'm going to draw that as my displacement vector. The box does indeed slide down the ramp. Got it. That's S, my displacement vector. Okay, but you're trying to prevent it from sliding down the ramp. So you either want to slow it down or you want to stop it, or you might want to even pull it up the ramp. Whatever you're doing, your force is going up the ramp as the box is sliding down the ramp. Okay, and this is your force. You're applying a force of 52 newtons. Okay, directed up the ramp. As the block slides down the ramp through a distance d equals 0.5 meters, its kinetic energy increases by 84 joules. Now, here's the question. The question says, if you weren't there pulling the block up the ramp, how much greater would the kinetic energy be? That's the question. So let me read that because that's kind of hard to read. This question says, how much greater would this box's kinetic energy be if you had not attached the rope and were trying to pull the block up the ramp? So you know what I'm saying that I'm going to say, I need to find the work done by me, the work done by this force, the force of the rope, F subscript R. Because if I know the work done by that force, then once I know that, then use the work done by that rope is equal delta K. And this is the answer. The answer to this problem is delta K. Because whatever change in kinetic energy is introduced by this rope, by the rope force, without the rope, that is the increase. All right, so let's step through this. Number 2, here is the work done by that rope force. It equals the rope force dot product with ds, switching. Again, we're not always going to switch. Sometimes we will just stay in dot. We're going to stay in dot product form when we use unit vectors, but I don't think unit vectors are today. All right, so here's the magnitude of the rope force times the magnitude of the displacement times the cosine of the angle between this is cosine of the angle between ds and the force. So theta, you can tell here theta equals 180. And as soon as you see theta equals 180, you can say, aha, work is less than 0. Negative work is occurring, which means, you know what that means? You know what work is less? This means change in kinetic energy is less than 0. And you know what that means? It means box or object slows down. All of that is true. Object slows down, and it's good to see the big picture like that. There's a lot. If work is less than, if I have negative work, I have a negative change in kinetic energy, which means the box slows down, which means that the velocity decreases. But so this is what my rope force is trying to do. Number 4. All right, so the work done by the rope force is equal to the integral of the rope force, which for me is 52 newtons, times ds times cosine of 180 degrees from 0 to d equals 0.5. Once again, let cosine figure out if this is going to be a positive or a negative result. You're always going to be specifying this as the smaller position value, and this will always be specified as the larger position value. And here's our answer. Our answer is the work done by the rope force is 52 newtons times cosine of 180 times the integral of ds, which equals s. So when I solve that integral of ds is s, and now you evaluate it across that boundary condition, 52 times cosine of 180 times 0.5, turn on calculator, 52 times cosine of 180 times 0.5 is negative 26. I get negative 26 joules. So number 6, aha. Rope force, rope steals, the rope steals, which means removes 26 joules of energy. That's what the rope is doing. So without the rope, if I didn't have that rope stealing that 26 joules, without rope, kinetic energy would be 26 joules greater than it is with the rope. So that's the answer right here, 26 joules. Short and sweet. So then you might be wondering, what the heck happened? Where did we use theta equals 51 and this, and where do we use these numbers? And the answers, I think of these as the expression is red herring. A red herring is basically information meant to distract you, to throw you off the trail. Okay, so this was never used, and this was never used. And maybe you could find a way to you could probably, but I didn't need them. I didn't need them for this approach. Okay, that's quiz 3. Let me get quiz 4 cooking. Quiz 4. Let me just double check. 1, 2, 3, 4 is 21. Chapter 7, quiz 4 is now available. And let's begin. Here it is. Chapter 7, quiz 4. A cord is used to vertically lower an initially stationary block downward. All right, so let's do this. Here is a block. This block is lowered by this rope. There's a rope attached to it. And this block is being lowered with a known acceleration. We actually know the acceleration at which this block is being lowered. It's saying the acceleration is downward, and it equals g/3. So they are giving us that information. That is the rate at which this block is being lowered, g/3, at a constant downward rate of g/3. So g/3 equals the acceleration. So without even, well, let's do free body diagram. We're going to have to do some force. So I'm going to do the free body diagram. I have tension. What is acting on this block? I have tension going upward. Tension, this is tension going upward. T for tension. Okay. T for tension. I have weight acting downward. This is weight. Weight acts at the center of gravity, center of mass. So this is weight's going downward. M, G. Free body diagram is done. Let's talk about a coordinate system. That's next. And remember the guideline. Do you know the direction of the acceleration? Yes, you do. the acceleration is down. So it's accelerating downward. I know the acceleration is downward. I actually know the numerical value. So that's all I need to hear. That's good enough for me. I'm calling plus y down. So remember this. This is still true. This is force analysis. So I'm going to call this plus y. Okay. So that's my setup. I'm lowering this box via a rope. I know the mass of the box. I know it's speeding up as it goes downward. And now the question says, when the block has fallen through a distance of 2.6 meters, so there's my displacement vector. I'm going to add that. Here is my displacement vector. From here, my block falls from here down to here. So this is S equals 2.6 meters. When the block has fallen through that distance, find the work done by the cord. All right, so let's jump into it. Number one, the work done by that tension force is the $sign for part A. What is the work done by that tension force? Pretty standard operating procedure. It's vector T dot product with vector ds, magnitude angle T, ds, cosine of the angle between them. Remember, this angle theta is always saying, it's always asking, what's the angle between that vector and this vector? And I know what those are. It's right here. This is 180 degrees. So the angle between my t vector and my displacement vector is 180 degrees. You can see that from the drawing. Maybe, I don't know, if I just relocated this. Here's my tension vector is right there, like that. Okay, my tension vector is going straight up. So if my tension vector is going straight up, like right there, and my displacement is going straight down, that's why I'm saying this angle is theta equals 180. Okay, number three, this seems to be so easy. The work done T, problems. What's T? What is T? Not to panic. Let's do force analysis method to the rescue. So I'm going to do a quick Y force inventory. My Y force inventory, which means you sum up all of those Y forces. And what do I get? I get negative T plus mg equals ma. Say something about acceleration. That's always your next step. So your acceleration statement is as follows. Your acceleration is equal to g over 3. That's given to you. All right, so let me make sure. My tension force is going up. My gravitational force is going down. So I counted for that. Up is negative y. Up gets a negative sign. Down gets a positive sign. Newton's second law says, hey, add up all of these forces, no matter how many of them there are. The result is mass times acceleration. So I'm feeling good about that. So let's solve for T, number 6. So that means T equals mg minus ma, or more specifically, mg minus m times g over 3. Or I'll just leave T, that tension force is mg minus mg is 2/3 mg. There, that's my tension force, brought to you by force analysis method. All right, number 8. Number 8, then, let's go back to number 2. Number 2, is now, here's my new number 2. The work done by that tension force equals the integral of T, and T now I can write as 2/3 mg. 2/3 mg. This is T. Let me just be careful. So I'm saying this is my tension force thanks to force analysis. And I got that. Got you. And then here's ds. And then cosine of theta is cosine of 180. Cosine of 180 degrees. So number 9, I guess solved. So you know what? The work done by this tension force. I'll let you finish this, but let's see. For me, this is going to be from 0, and it's lowered 2.6 meters to 2.6 meters. Okay, let's get this one correct. Do I know M? I do. It's 13. Okay. Negative 220.82 joules. This is the answer to part A. Okay, done with part A. Part B says, what about gravity? Ooh, that's going to be easy, I think. Let's just knock that out. Part B says, what is the work due to that gravitational force? That's the $sign. So right away, I'm gonna go right to magnitude angle. The work done by the gravitational force is the integral from 0 to 2.6 meters times the gravitational force, which is mg. That's this force right here. I am looking at this gravitational force times the displacement, which is ds, times the cosine of the angle between them. So here's the question. What is the angle between this gravitational force right here, which is going straight down, and the displacement, which is also going straight down? If they are both going straight down, the angle between them is 0 degrees. Okay, so let's punch that into the calculator. The work done by the gravitational force is equal to 13 times 9.8. 331 some change. 331.24. That is the answer to part B. Done with part B. Part C, what's the kinetic energy of the box? So thank goodness for the work kinetic energy theorem, because it's a simple matter of applying the work kinetic energy theorem. So part C wants you to find out kinetic energy. The kinetic energy equals $sign. And from the work kinetic energy theorem, from net work is equal to the change in kinetic energy. This is, once again, this is the work kinetic energy theorem. A cornerstone, a pillar of the community. This is a work kinetic energy theorem. Okay, so here goes. The net work done on this object is comprised of the work done by that tension force plus the work done by the gravitational force, and it equals delta K, and delta K is final minus initial, and you know the initial is 0 because it starts from rest, because it says initially stationary. So initially stationary means this is equal to 0, And that's the answer. So you know, you have a value for the work done by the rope or the cable, the work done by the gravitational force. This is equal to 0. So there you go. So it's going to be line 12 divided by line 9. So what is 331.24 plus a negative 220.82? It's 110 and some change. So step 16. That's the kinetic energy. Kinetic energy is 110 joules. And that's the answer to part C. Let's do part D, 16, 17. Part D is asking, what's the speed of the block? So speed is the $sign. And good news is, remember, kinetic energy is defined as 1/2 mv squared. So let's just solve for v. When I do that, I get v. Let's see. Because I know kinetic, let me make sure. I know kinetic energy. Yes, I know m, 13. All right, so solve for v. .1 and some change. 4.1 meters per second. You do the dimensional analysis. You do the dimensional analysis. Because you should get, we did this before, and you will get meters per second, but you should do it again. But for now, that's the answer to part D. We are done with this problem.
Hey, Professor.
Yep.
Hey, so I got B through D, but for step A, when I was crunching my numbers, my number that I got for my work total came out wrong on my plus, even though I had like the same steps as you did for finding my total work.
Let's see.
Yeah, I have the same problem as well.
Let's see.
A is not seeming to let me put in the right answer.
Was your number G over 3? So, Will, did you have G over 3?
I had G over 2. So my equation in step 8 would have been the integral of my distance, and then it would be my mass times gravity. So I wouldn't have the 2/3 there because the 2 over 2 would cancel out.
So you had negative T plus mg equals mg over 2, which means for you, T is going to equal mg over 2. So you used mg over 2?
Yeah, I just want to make sure I got this right.
Okay, and then here, then for you, the work done by that tension force, not like that. The work done by your tension force is going to be the integral of tension, which is mg over 2 times ds times cosine of 180. And how far did your block fall?
Just make sure I got this right. So I do it one more time. Make sure this is right. So yes, I plugged that in. My my total distance that I thought was 2.4 meters, and then my answer came out to be negative 26.656 for the work.
What was
joules.
What was the distance that your block fell?
It was 3.4 meters.
3.4 meters. And then what was your mass?
Mass was 1.6 kilograms.
1.6?
Yes.
Okay, 1.6 kilograms. So then you're going to do 1.6 times 9.8 divided by 2
2.
times 3.4 times cosine negative 26.656.
Yeah. So I had refreshed I tried everything, didn't work. So I exited out, went back in, tried the same thing with negative 26.656, didn't work. I just exited out and re-entered a third time, and it finally worked. So I'm not sure why.
Yeah, I don't know either. Yeah, because I mean that's the right answer. So
yeah, there we go.
I don't know.
It finally worked.
Because I'm like changing things on my. But I don't know. I don't know why that happened, but you're not making any mistakes. So again, here's the good news: is you got complete correct credit. That's good, and that's good for everyone. You just have to look at this. Right now you have to stare at this page, and you have to go through steps 1 through 20 and say, what is it? What is there in steps 1 through 20 that seems perplexing? I'm going to set up quiz 5. 1, 2, 3, 4, 5 is problem 23. Quiz 5 is problem 23. Chapter 7, quiz 5. Making good time here. These are pretty short problems. I mean, in general, you guys, you'll find that energy analysis is much more economical than kinematics analysis or force analysis, which is good news because most times you can do things via energy analysis. Not every time, especially if you're asked to, hey, do this using force analysis like chapter 6. But chapter 7, quiz 5, 1, 2, 3, 4 is problem 23. That looks good. That looks good. All right, you should now, hang on 1 second. And it is available now. Chapter 7, quiz 5. Maybe do some extra refreshes just for safety's sake. Okay. So this is what I believe is chapter 7, quiz 5. All right. What time is it? Yeah, geez, time seems to be flying by. Okay. You are applying a force. You are applying this force to this shoebox. It's called a shoebox. When you apply this force to a shoebox, this box moves up a ramp. So let's draw the upward. So this box moves up the ramp like that. This box is moving up the ramp, but you know what? They actually don't give me this S vector, but that's the displacement of the box. And I know this is, I got an angle, so I know what this angle is. It's frictionless. Constant speed, that's got to be important. Well, I'm thinking it is. Constant speed means it doesn't speed up, it doesn't slow down. You know what else this means? You know what else constant speed means? It means there's no change in kinetic energy. It's moving, but there's not changing kinetic energy. And then here's the dollar sign. FA equals the dollar sign. That's the sorry, that's not the dollar sign. The dollar sign is the work done by this applied force A. That's the dollar sign. Okay, so now what? But here's the interesting thing. It says when this motion takes place, they don't tell me this S vector, but they just say, they says the box has moved up through a vertical distance of h equals 0.25 meters. So you know what that means. It gets a little more complicated. Here's this vertical distance vector right there. That's the vertical distance. And this then is the horizontal distance. So thanks to vector decomposition. All right, so this is what's happening. All right, so this is H. This is H. Okay, that's H. So now here's my conundrum. Well, I know this is 90 degrees. Do I know this angle here? No. Do I know this angle here? No. I don't know that angle. So I'll start numbering. Number 2. Uh-oh. I don't know. I don't know angles. I don't know triangles, angles. So I'm starting to have a minor panic attack here. Now what? I'm not sure. I'm just going to go on. I'm going to fight the good fight and say, well, the work done by this applied force FA is the integral, and I'm going to go right to magnitude angle. What is the magnitude of my applied force? It's FA. What is the displacement? The magnitude of my displacement. What's the cosine of the angle between them? Cosine of theta. And I'm going from 0 to I don't know. So this is kind of a dead end. Dead end. Because I don't know I have too many unknowns. I don't know I don't know the angle, and I don't know the displacement S. So panic. Number 4, start to panic. And then as you're panicking, just let's try work kinetic energy theorem. Let's try the work kinetic energy theorem says the net force, the net work done on that shoebox is equal to that shoebox change in kinetic energy. Okay, so I'm just trying this because I don't have any other ideas. The net work done on this shoebox is going to be a combination of the work done on the shoebox by gravity plus the work done on shoebox by force F subscript A. And whatever that is, that's delta K. And aha, delta K equals 0. Delta K equals 0 because of this. Constant speed means there is no change in kinetic energy. No change in kinetic energy means delta K is equal to 0. So let's run with that. So you know what I have? The work done by that gravitational force is going to equal negative of the work done by that external force FA. So here's my answer. The work done by this force that you're applying, F subscript A, is negative the work done by gravity. So that's my way out, I think, because now I'm going to say, what's the work done by gravity? Let's do, this is hopefully looking pretty darn repetitive, which is good. Okay, it's going to, the work done by gravity is the gravitational force. I'm just going to go back to dot product just because it's been a while. Times the displacement, ds, times, there's gravity's going down, ds theta. Okay, times ds times the angle between gravity and ds theta. Oh, sorry, I'm getting ahead of myself. Let me go to magnitude angle. So this is going to be from 0 to S of FG times ds times the cosine of the angle between them. And now here's the problem again. What is this angle right here? this angle, I don't know. So theta right here is theta equals, I don't know. Okay, theta is unknown, but I do know this dimension right here. I know this dimension right here, that dimension S. Okay, so this gets a little bit triggy. So we're trigging out a bit here. Whatever this, I don't know this angle, but I know that angle. All right, so I can say this. Let me go to step 8. Step 8, the work done by gravity is equal to, I'm going to change, it's going to be from 0 to h times FG, which is mg, times dh times cosine of 180. All right, so let me fine tune this. From h is 0.25. Okay, so here's my gravitational force. My gravitational force is straight down like that. There it is. There's my gravitational force. Here's my vertical displacement force, H. H is going straight up like this. There's H. Here's theta. This is 180 degrees. So this theta equals 180 degrees. Let's get the right answer. Then we'll come back and do a little more chit chat about this. Okay. H, this looks good. I think that's all good. Number 9. So the work done by gravity is going to equal mg, which is 4 times 9.8 times 2.25 is negative. So this is negative 9.8 joules. And remember, the work done by that applied force is equal negative work done by gravity. Okay, so that's the right answer. I need to go back and just tighten up some loose ends though. All right. HS. If I'm looking at this triangle, I'm going to look at this triangle. And I'm saying H cosine of this angle right here is the same as the sine of this angle. So if this is angle theta, let me, I'm kind of talking to myself because I need to insert a few trig justifications. All right, this is angle A. This is angle 180 degrees minus angle A. Okay. So let's see, the cosine of angle A equals, let's see, let me double check this. 150, 130, 30, cosine of 30 equals negative cosine of 180 minus A. That's the trig identity I think I'm looking for. Okay, 180 minus. Okay. I'm trying to remember this trig identity. Cosine of 180 minus 30. Okay. Cosine of 30. All right, so this is the trig identity I'm looking for. So I didn't know that this is the angle between my gravitational force and my displacement vector. It's angle A. I don't know cosine of angle A, but whatever cosine of angle A is, it's the same as cosine of this angle right here. All right. So that's how I can use, if I look at this triangle, cosine of 180 minus A equals side adjacent, which is H, over hypotenuse, which is S. So from there, this is how I'm saying, this is how I'm making my substitution. Okay, so that's enough trig. I just wanted to verify that. That's the answer to part, no, there is no part B. This is the answer to the question. Okay, that's problem 23, or problem 23, chapter 7, quiz 5, with a little trig odyssey detour. Let's do, let's take a 7-minute break. So I will see you at 3:04. See you at 3:04. And we're back. I was haunted. I still didn't have the comments tight enough for this problem. So especially when you rewatch the recording of this video, I want to be on record for perpetuity that I've added this commentary. Otherwise, if I was grading myself, you know what? I would write down, can't follow your work. How did you get from here to here? So I'm just taking this moment to say, okay, and I'm doing this for the recording, but let's listen here now. This is the work done by gravity. Straight up magnitude angle expression for the work done by the gravitational force. That's just generic. And then I'm saying, well, I don't know angle B, but I don't know angle A. That's unknown, but I do know angle B. Angle B is 180 minus A, so that's true. So then I go from step B to step C. So step B becomes mg ds cosine of A is equal to negative cosine of 180 minus A. This is a trig identity that I had to spend a minute to kind of remember what that is. And from C to D, I'm saying I'm bringing this negative sign out of the integrand. So this negative sign ends up over here. Here's mg ds, and I'm saying this is cosine of B. Cosine of B is 180 minus A. And this is what's equal to H. ds times cosine of B. If I look at this triangle right here, if I'm looking at this triangle right here, and I say to myself, what's the cosine of B? It's side adjacent over hypotenuse. Side adjacent over hypotenuse. And that's how I'm saying S cosine of B, angle B, equals H. And that's how I get this expression right here. This expression is the work done by the gravitational force. All right, there. Now I'm on record. This is now officially airtight. I would have to give myself full credit because I have talked about every step of the way. What a great day to be a physics student. Let's do this problem. We're doing pretty good on time. All right, so this should be chapter 7, quiz 6. Now we introduce ourselves to the spring force. Spring force, which is a new kind of force. There's a bunch of stuff. Okay. So let me get rid of this. we actually add to our list of force. I don't think we've dealt with the spring force before. I think if I remember correctly, I don't think we've been introduced to the spring force before chapter 7. Okay. So if I just want to remind me, what kind of forces? Let's take a little inventory. What kind of forces have we dealt with? We've dealt with the normal force. We've dealt with tension, kinetic friction, static friction. What else? Is that it? Those are the only forces we've dealt with. I guess so, maybe. And now we add to this list weight force. We've dealt with weight, W equals mg. We've dealt with the weight force. And if I'm forgetting something else, maybe. But we're going to add to this list now the spring force. F sub S equals spring force. Spring force. That's the spring force. Springs. And it turns out springs are really interesting, not because of springs, but springs actually, the analysis that you apply to springs is very much found in electrical engineering, quantum physics, mechanical engineering. And a good example of a mechanical engineering would be automotive suspension. But in general, it turns out that many things in nature behave like springs. So this is why understanding spring force is so important, because there are many things, both in an exotic sense and a very practical sense, that behave like springs. All right. And we'll get into a lot, especially in chapter 15. But we're sort of getting a little taste now of why springs are so darn interesting. So let's start. Here's the expression. This is I believe this is chapter 7. There's something called Hooke's law. So I'm gonna kind of fast track through this, because your job is to thoroughly digest those lecture videos well before the exam 2 date. Here's Hooke's law. F, the spring force, is given by negative kx, where this stands for stiffness constant. Spring, this is the spring stiffness constant. For example, the spring that is attached to my garage door is a very massive spring. So that, because it has to apply a lot of force, because the garage door is heavy, and that garage door is, needs to be guided or managed, in part at least, by a spring. So this is a very stiff spring. Whereas what's a very weak spring? If you ever, let me see if I can find a picture. I used to always do this. I think this was a personality disorder. I used to always take apart ballpoint pens. Because you could actually make kind of like launchers out of them. Ballpoint pen spring. So here, this is what I'm talking about. Here's a picture. Let me call this up. There. Let me share this. All right. So from Amazon, you can get these ballpoint pen refills, medium for tactical pen, and more. All right. So with a spare spring. So these are spring activated. They retract. You press a button, you press them down to extend them. You press it again, and the spring retracts them. So this is a small spring, not a lot of stiffness there, but there's a wide variety. There's a wide variety of spring types, and I'm saying that K, whatever the stiffness is, K stands for the spring constant. So, for example, a K of 1 Newton per meter is what I would call loose. A K of 5,000 newtons per meter is pretty darn stiff. Again, think of your garage door spring, and there's much more intense springs than that. Stiff spring, loose spring. All right, this is this negative sign right here. This means the spring force is a special term. Restorative. The spring force is a restorative force, which means springs always want to go home. They always want to go home, meaning they always want to go back to equilibrium. Back to equilibrium. So that's what that negative sign means. If you compress a spring, the spring wants to elongate. If you elongate a spring, the spring wants to compress. The spring always wants to do whatever it needs to do to get back home. Okay. X, this X value here, this is the amount of compression or elongation. Okay, so now you have been formally introduced to Hooke's law. A lot of times you ignore that minus sign because you let your vectors do the talking for you, but let's proceed. We have a spring mass system. A spring mass system means you actually have a mass attached to a spring. So I guess that's as good as it's going to get. All right, so let's do the read through. This is what you do. You walk up to this block and you crank this block back from 0. And what does 0 mean? X equals 0 means this is the equilibrium point. Equilibrium is at X equals 0. And you stretch it to X equals 3.0 centimeters. So this is the, in this case, this is the amount of elongation. Okay. All right. And when you stretch it to this value, you're holding it stationary. The second figure gives the work that our force does on the block. So that's referring to this graph. And then we're going to do some things. But right here, this is saying this graph, this is work versus position. That's what this graph is. And you know what my graph is saying? My graph is saying at X equals 3 centimeters, because that's where we stretched out to. X equals 3 centimeters equals 0.03 meters. When I stretch this spring from here, one second. Okay. When I grab hold of this spring and I crank it back 3 centimeters, X equals 0.03 meters. I get this much force. The spring, so if my displacement is X equals 0.03 meters, this is what my spring force is doing. Springs don't like that. Spring always wants to go home. So this is my spring force right here. This is F subscript S. Okay. So according to my graph, at X equals 3 centimeters, when I pull that 3 centimeters to the right, I get this much work. Work equals this much. I get this much work right here. Let's take a look at that. This much work. How much work is that? I'm not at the top of that graph. I'm right there. Good. Right there. So let's count off these boxes. All right. So let's see. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 boxes. So from a scaling factor point of view, WS equals, for me, WS, they give me a WS value of 2 joules. So WS is given as 2 joules. It's just a scaling factor. And 2 joules apparently corresponds to 10 boxes. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But I'm not at box 10. I'm at box 9. So if I'm at box 9, I would just do this conversion factor. I would say, let's see, 9 boxes times my conversion factor, 2 joules per 10 boxes. That's my conversion factor. from here equals 1.8 joules. So that's my answer. When I've stretched this, when I've cranked this mass 3 centimeters to the right, this is how much work was performed by my spring. My spring is trying to pull leftward. Work is equal to 1.8 joules. This is work done by spring force. Not by me. I'm doing some work, but we're looking at what's going on with the spring. I'm doing positive work. The spring is doing negative work. But for right now, that's how much work. According to this graph, I can safely say that from 0 to 3 centimeters, I have done 1.8 joules of work. Good to know. In your green sheets, and I guess more importantly, from the lecture video, the spring work. This was a pretty detailed derivation. And I'm telling you, if you are interested in a career in science or engineering, you have to learn the derivations. It puts you in category A. So that's another hoop to jump through to get yourself out of category B and into category A, where again, the sky is blue and the grass is green. So the spring work derivation said the work done by the spring force equals 1/2 K X initial squared minus X final squared. So can't wait for you to view that, and you should have already, in a perfect world, you've already understand where that derivation is coming from. You don't have to memorize these derivations. You just have to be able to follow them, because that's recyclable information. All right, so what can I do with this? Because part A says that once you pull it to 3 centimeters, you are going to do another displacement. You're actually going to pull it to X equals, we then pull the block out to X equals 5 centimeters. So then, as if that's not enough, you're going to pull this out to X equals 0.05 centimeters. And then you let go. So this is the sequence. Step 1, pull the block 3 centimeters to the right. And then let's learn what we can learn from that segment. Segment number 2, you're going to pull it another 2 centimeters, I guess I should say. This is 2. You're going to pull it an additional, no, I guess I have this right. No, you're going to pull it an additional 2 centimeters. So this box is now going to go from X equals 3 centimeters to X equals 5 centimeters. And then you're going to let go. And when you let go, part A says, how much work did the spring do when the block goes back? You let go of the spring. Springs always want to go home. So this spring force is basically going to go in this direction. It's sitting here at X equals 5 centimeters, and it's going to head to the left because springs always want to go home. And the question says, what is the total amount of work done by the spring at this point right here, when it once again returns to X equals 3 centimeters. All right, so what I'm going to get from this, I think from the first segment, from 0 to 3 centimeters, I think I can get the spring stiffness constant. So I'm going to go with that. Find the spring stiffness constant, which is K. K is the spring stiffness constant. Let's do that. So I have this. From X equals 0 to X equals 3 centimeters, I've got work equals 1.8 joules per the analysis below. There it is. And work is also given by this expression, 1/2 K X initial squared minus X final squared. Okay. So, all right, let's go ahead and find K. So therefore, if I solve for K, K equals work, I guess 2 times W all over X initial squared minus X final squared equals 2 times 1.8 joules all over 0.03 meters squared. So this is the spring stiffness constant. 2 times 1.8 divided by 0.03, 4,000. I get a value of 4,000 newtons per meter. And once again, that's my K value, and that's not going to change. So I can use that going forward. K. I'm going to look up something. Give me a moment. I want to look up something in the old lecture notes. I got to double check. Chapter 7. Chapter 7. Okay, there it is. Let me just, here's the lecture notes, kinetic energy, work kinetic energy, spring force, there's the spring force. Okay. All right, I just wanted to double check this expression. Okay. So now that I know my spring force is 4,000 newtons per joule, now the floodgates can open and we can really knock down all these questions. So step number 5 says, all right, release, when I release this block, release at X equals 5 centimeters and calculate the work done by the spring force when the object reaches X equals 3 centimeters. That's the job right now. Part A says you pull it back to 5 centimeters, you let it go. What's going on? How much work does the spring do on the block when it hits 3 centimeters? So number 6, ready? The work done by the spring force is 1/2 K X initial squared minus X final squared. And you know all of these numbers. So the answer is 1/2 times 4,000 newtons per meter times X initial squared starts off at 0.05 meters squared minus X final ends up at 0.03 meters, 0.03 meters squared, and that's the answer. And you do dimensional analysis to get joules. So what is okay, 3.2 joules. I don't have my answers here, but you tell me. All right, so this is 3.2 joules. This is the work done by the spring force from when the object goes from 5 centimeters to 3 centimeters. So this is the answer to part A. Part B, let's go ahead. Number 8. Part B is saying you release it again from 5 centimeters. What's going on when it hits -1 centimeter? So this is from x equals 5 centimeters to x equals -1 centimeter. What's the work done by the spring force? This is what we're after in part 8. So this is kind of plug and play, but this will be interesting to analyze. Very easy calculation. The answer is the work done by the spring force is 1/2 K, 4,000 newtons per meter, x initial squared. X initial is still starts off at that 5 centimeter mark, 0.05 meters squared, minus, and it ends up at -1, -0.01 meters squared. And that's the answer. So we've made quick work of that. We just have to talk about it. For part B, the work is 2,000 times 0.05 squared minus 0.01 squared, 4.8. Interesting. This is the answer to part B. We need to talk about this. Part B. So this is what's perplexing to me, or this is why I'm thinking on it. So here's the floor. Here's the object right here. Here's the spring. My spring is doing this. That's my spring. And my object goes from x equals 5 all the way to x equal 0. So this is 5 centimeters. This is 0 centimeters. And then it keeps going. It actually continues to go past the equilibrium point all the way to -1 centimeter. So let's talk about that from during this phase right here. From x equal 5 to 0. From x equal 5 to 0. Here. This is all positive work. Why is that considered positive work? Because this is my displacement, S, and my spring force is also going to the left. Springs always want to go home. So I'm saying from 5 centimeters to 0 centimeters, that's positive work. From 5 centimeters to 0 centimeters, comma, work done by the spring force is greater than 0. Because look, the purple vector is lined up with the orange vector. Theta equals 0. That's why. However, from 0 centimeters to -1 centimeter, so from here to here, my displacement is still in the negative direction. So my displacement is leftward, but, and this is the big difference. Having said that, my spring force is actually going to the right. Why is that? Because springs always want to go home. So if you push me to the left, I want to go back to the right. If you push me to the right, I want to go to the left. So now in this case, you have negative work done. Here's my purple spring force. This is my displacement. And in this case, theta equals 180. So I do have positive work and negative work, but look at all this positive work. So this is a huge amount of positive work from 5 centimeters to 0 centimeters, and then from 0 centimeters to -1 centimeter, work is less than 0, but it's not as much. Going from 0 to -1 is a lot less than going from 5 to 0. All right, so to conclude, part D. part D says, what's going on if the spring bounces all the way to the left to the -5 centimeter mark? So let me do this, maybe just some conversation. So this is part D. Here's the floor. Here's the object over here. And now that's the object. Oh, trouble. Uh-oh. I've restarted. Okay. So now my box is going to go from x equals 5 centimeters, which is right here. It's going to go from there all the way over here. So I'm going to go from 5 centimeters to 0. This is 0. This is 5 centimeters. And I'm going to keep going from 0 to -5. All right, so this is positive work right here. This is positive work, so work is greater than 0. This is negative work. Work is less than 0, and you should know why. I'll let you review this and make sure you know why. Number 11. So the spring force is once again 1/2 times K x initial squared x initial squared minus x final squared -0.05 meters squared. And that's the answer. So this equals 0. There's no net work. There's no net work done. Even though a lot's happened, the net amount of work is 0, which means there's no change in kinetic energy. I'm going to write that down just for the interest of it. There's no change in kinetic energy for part D. And that, what time is it? 3:37. Okay, and that is quiz 6. Let's see. So here, let me leave this here for a minute. You can noodle on that as I look. Let's see. 1, 2, 3, 4, 5, 6, 7 is 31. Let's take a look at that. Seven is 31. We'll do one more. We'll do one more. We're going to finish early, which is unheard of. 7:31. Chapter 7. Quiz 7. Chapter 7. Okay, I think it's good to go. Last quiz of today. Chapter 7, quiz 7. We're making good time. Chapter 7, quiz 7. Okay. Ooh, this is a job for calculus, I think. I think this is a job for calculus. The only force acting on this object as it moves along the positive axis, the positive x-axis, is given by a variable force. So this is something. Let's do calculus. Okay, so I need to do my drawing. Here's my object. My object is sitting right here, and it's being acted upon. The only force acting on this body as it moves along the positive x-axis. So it's moving like this. It's displacing according to this displacement vector. Got it. This is my displacement vector because it's saying it's moving along the positive x-axis. But as it's moving along the positive x-axis, there's apparently a force that's getting bigger and bigger. The more I go to the right, the bigger this leftward force is going. So I'm going to draw that looking like this. This is Fx for me equals negative 4x newtons, negative 4x newtons. So you can see the further my box goes to the right, the greater the leftward force becomes. It grows. It grows in the negative x direction as the box moves to the right. Where x is in meters, okay, the velocity of the body. So I'm saying the velocity of the body. So the velocity at x, the velocity at x equals 2.7 meters equals 9.1 meters per second. So we know that. Part A says, what is the velocity at 3.8 meters? So the velocity at x equals 3.8 meters equals $sign. All right. So my box apparently is moving to the right. And here's the question. When my box, so if I call this might be 0. This is x equals 0. And then we know at x equal 2.7 meters, the velocity at this point is equal to 9.1 meters per second. Okay. Now, what's going on? As apparently my box is going to keep moving to the right. And my guess is as it's moving, I'm thinking as it's moving to the right, it's slowing down. Because I know one thing, acceleration is in minus x direction. I know that. If the force is pointing in the minus x direction, the acceleration has to be pointing in the minus x direction. You know what that means? Slowing down. Slowing down body, box slows down, I think, unless I'm thinking of this wrong. Box slows down from x equals 2.7 meters to x equals 3.8 meters. That's my thinking. All right, so when the box does get to this point, x equals 3.8 meters, the velocity at this point is $sign. Okay, so with all that said, let's start doing this. I'm thinking work kinetic energy theorem for obvious reasons because I got nothing else. So this is the net work done on this object is equal to the change in kinetic energy. And this becomes the net work done is F times vector F dot product. No, I'm not going to stick with dot product. I'm going to go to magnitude angle just because I'm still not, I could use dot product, but I'm still not really given unit vectors. So F ds cosine theta, that's the work done due to this force, equals K final minus K initial. Let's keep going with that. All right, so let's just sanity check this right now. This force here, let's do a sanity check. This is going to equal 4x. I'm not going to use that negative 4x. That's the job of cosine. All right, what's the cosine? As the box moves rightward, as the box is moving from 2.7 meters to 3.8, it's moving to the right. Specifically, if I wanted to be maybe a little bit more precise, the box is moving from 2.7 meters to 3.8. So maybe this is the better S to consider. I'm going to get rid of this. Good enough. There's my S vector. And you can see that angle is theta equals 180. The angle between my blue force vector and my red displacement vector is 180. Theta equals 180 degrees. So number 3, let's keep going with this. The integral of 4x times ds times cosine of 180 equals K final. K final is I don't know, and that's kind of my dollar sign, minus K initial. K initial is, we know what that is. It's 1/2 mass times V initial squared. Okay, so there's stuff going on here. This is my K initial. K initial is right here. So I'll just add to this little area here. K initial equals 1/2 MV initial. This is V initial squared. Let's get a number on that. 0.5 times 2.6, my mass is 2.6, times the initial velocity is 9.1 squared. So I get 107 and some change. This is my initial kinetic energy, 107.653 joules. That is my kinetic energy. Let me just do a double check. 0.5 times 2.6 times 9.1 squared, 107.653. Good to know. Good to go, I guess. All right, let's keep going. I'm going to make one other substitution here. This ds vector, I'm going to call this dx. So I'm going to switch my variable of integration from ds, which is just some generic label term, to dx because I am specifically moving in the x dimension. And I'm thinking this is the variable of integration for this force. So I have to use a variable of integration of dx to go along with my 4x for my force. So number 4, step 4, what do I have? On the left side, I have negative 4x squared over 2 equals K final minus 107.653 joules. Let's talk about that. I think that's right. Okay, number 5. So that means I have negative 2x squared. Oh, sorry, I got to back up. Stop the presses. Stop the presses. I forgot about my limits of integration. My limits of integration. I'm starting off at x initial equals 2.7 meters. I'm ending up at an x final location of 3.8 meters. Okay, so there's my boundary conditions. Now I can solve the solution. What is the integral of 4x dx? The answer is 4x squared over 2 equals 2x squared. And I need to evaluate that across this boundary, 2.7 to 3.8 equals, let's do that, 3.8 squared minus 2.7 squared times 2, 14.3. Okay, and I can't forget that cosine of 180. So that makes that negative. Okay, let me double check. 3.8 squared minus 2.7 squared times 2, 14.3 negative equals. So all of this was my integral. So just to be a little more, this was, I guess I'll leave it like that. This is step 4. And this equals K final minus 107.653 joules. Let me annotate this for clarity. So this is K initial. Got it. This is K final, which my dollar sign is living in there. This whole thing here was the integral of 4x dx cosine of 180 from 2.7 to 3.8. Okay, just to add clarity, because things are getting crazy. All right, so K final. K final equals 107.653 minus 14.3 joules. And K final is also 1/2 mv squared. Okay, number 6, solve for VF. VF equals 9.66. Hang on 1 second. Okay. $2.7, 9.1, 3.8. I think I made a calc error somewhere. Let me go back and debug a bit. And you can debug along with me because I'm getting the wrong answer. So I made a mistake somewhere. 2.6. Oh, I think I found it. I did find it. Sorry. 107.653 minus 14.3 times 2 divided by 2.6 square root. Okay, there. I didn't make any mistakes. I made a calculator mistake. So my final velocity is 8.474 meters per second. The mistake I made is I forgot to multiply by 2 and divide by m. All right. All right, so that's part A. So pretty good calculus problem. And you knew this was going to be a calculus situation as soon as you saw the function. So that's as soon as you see a function, you switch from algebra mode to calculus mode. Okay, part B says, at what positive value of x will the body have a velocity of 2.2 meters per second? I don't know. Okay, so let's figure that out. At what, I think we can recycle a lot of stuff here. Number 8, part B is saying at what? At x equals $, v equals 2.2 meters per second. This is part B. I think we can recycle some stuff here. So I guess I'm going to say, I guess I'm going to keep these same initial conditions. All right, so let me just, this is my initial condition. I know at I know what's going on at 2.7, at the 2.7 meter mark. I have this much velocity and this much kinetic energy. So now I have to say, okay, I'm going to let the force do its thing, and it's going to slow down. So my guess is this box is going to continue to slow down as it goes to the right. So I'm just going to say, well, this box is going to keep going to the right, and at some point right here, it's going to slow down some more. And let me erase this. At this location right here, this is x final equals $, v final equals 2.2 meters per second. Okay, so we're after that $xf. So let's keep going. Step 9. Where can I just pick up here? I guess I'm going to, let's rewrite number 3. Let's reuse number 3. Here's number 3 again. The integral of f, which is 4x dx, it's still cosine of 180. But now I have x initial equals 2.7 meters, just like before. And x final equals, I'm just going to call it x. I don't know. This is my $. And that is the amount of work done by the force applied to this object. And that equals k final minus k initial. Step 10 is, all right, the integral of 4x dx is still going to be 2x squared. So if I solve the integral, I have the integral of 2x squared evaluated from 2.7 to x final, cosine of 180. So I'll just, cosine of 180 is negative. All right, equals k final. Here's k final. 1/2 mass times v final squared. Here's k initial. 1/2 mass times v initial squared. And if I factor out 1/2 mass, v final squared minus v initial squared. Okay. So let's evaluate this. It pays to be meticulous, obviously. So I have -2 times x final squared minus 2.7 squared, okay, equals 1/2 mass. My mass is what is my mass? My mass is 2.6 kilograms. 2.6 kilograms times v final squared And with my new updated situation, my final velocity is 2.2 meters per second, 2.2 meters per second squared minus my initial velocity, which is that 9.1 meters per second squared, minus 9.1 meters per second squared. All right, solve for find XF. Okay, so here we go. Okay. Interesting here. Let's see, I get XF equals plus or minus 7.61 meters. So what is it? What, oh, it says at what positive. So they tell you that it answers my question. They said at what positive value. So XF equals 7.61 meters. That's the answer to part B. And we are completely done, or soon to be. Congratulations. You have just finished 7 quizzes. We need to have a very constructive conversation on Thursday about how a lot of you need to change your approach to prepping for an exam. And that will be a very constructive conversation. All right, so let me zoom out. There. That's this problem in its entirety. I'm good to go. Look, it's 4:01. We're knocking off early. It just doesn't seem right. But that's 7 quizzes, and I'm kind of out of gas. I need to take more vitamins. All right, so that's it for me. There's 7 quizzes now that you guys probably, here it is.
So for number 4, why isn't 2x squared negative 2x squared?
Because it should be. Let me do that. That's great attention to detail. Negative 2x squared. You're right, because that should be negative. This should be negative because that's what this cosine of 180. Yeah. So that's a good correction.
Okay.
Good point. Okay. Let me just double check. Is that 3.8 squared minus 2.7 squared
2.6
times 2? Yeah. Okay. So that's good. That's a good correction. All right. Does before I sign off, does anyone need me to leave any one of these screens up and running? Or are you good to go as far as these 1, 2, 3, 4, 5, 6, 7?
You leave 6 open just for a little bit.
The screen or the quiz?
The quiz.
The quiz. Okay. All right. So it's now 4:04. I'll extend it till 5 o'clock. Quiz.
Sounds good. Thank you.
All right. So I'll see you guys on Thursday.
A quick thing.
Yep.
My partner and I didn't get our Excel sheets turned in for the lab 2 weeks ago.
What lab was that?
That was the one with like the cart.
Yeah, the carts. Yeah.
Yeah.
Why didn't you turn it in? Did you forget, or you didn't have it ready?
We didn't have it ready.
That's okay. All right. That was for chapter 6. So that's fine. Email it to me as an attachment.
Hey, Professor.
Okay. Is that good, Lewis?
Yep.
All right. Good.
So I'm just trying to figure like why my numbers just don't.
Well, we'll do this. I'm going to bounce off and just take care of some pressing business. Post something in the group chat if you need me to jump in and lend a hand.
Okay.